we'll be discussing in this lecture is tunneling and encapsulation. Actually, a tunnel establishes a virtual connection for data packets uh, between a tunnel entry and an endpoint. Tunnel establishes a virtual pipe for data packets between a tunnel entry and a tunnel endpoint. Packets entering the tunnel are forwarded inside the tunnel and leave the tunnel unchanged. Okay. So tunneling, that is sending a packet through a tunnel, is achieved using encapsulation. Sending a packet through a tunnel is achieved using encapsulation. Encapsulation is a mechanism of taking a packet consisting of header and data and putting it into the data part of a new packet. Okay. Take a take a packet which has the header and the data which has the header and the data. So if you take this packet, it has the header part and also it has the data part. Now put this entire packet into the header into the data part of the new packet. So put this entire packet into the data part of the new packet. Okay. So that is called as encapsulation. And the reverse operation of taking a packet out of the data part of another packet is called decapsulation. Taking a packet out of the reverse operation, that is taking a packet out of the data part of another packet, is called decapsulation. Okay. So in the reverse end, so now this new data is nothing but the combination of original IP header and original data. Now you take this new data and again from this you identify what is original IP header and what is original data. That is, you pick up that packet. So that process is called as decapsulation. And this encapsulation and decapsulations or operations typically performed when a packet is transferred from a higher protocol layer to a lower layer, or from lower layer to a higher layer. So when it moves from higher layer to lower layer, encapsulation is done. And when it moves from lower layer to higher layer, decapsulation is done. Okay. So that is what is shown in this diagram. Okay. So there are different types of encapsulations available, like IP in IP encapsulation, minimal encapsulation, uh, and generic routing encapsulation. Okay. So let us discuss IP in IP encapsulation. So this is an example of IP in IP encapsulation. Okay. So this diagram is an example of IP in IP encapsulation. IP in IP encapsulation is a mandatory encapsulation scheme for mobile IP. For mobile IP and IP encapsulation is a mandatory thing. Okay. So in this figure uh, you can see a packet inside the tunnel. You can see a packet inside the tunnel. So only inside the tunnel encapsulation is done. So there are so you can see there is a this is there are two packets. This is one packet. So it has this is the header port of this packet. I'll call it as head H. Okay. So this is the header port of this particular packet, and this is its data port. This is the data port. Okay. And there is another packet, and there is another packet which starts from here. Okay. And for this packet, this is the header port. This is the header port. Okay. And this entire thing is the data port. Okay. Whereas for this particular packet, That is for this particular packet. This is the header port. Okay, this is the header port, and this is the data port. This is the data port. Okay, so there is one packet inside another packet. Okay, so this header you can call it as inner header, and that header you can call it as outer header. Okay. So here basically we have a packet inside the tunnel. The fields follow the standard specification of IP protocol. Um, so the fields of the outer header are something like this. The version field has a value of 4. So at the top you have the outer header. First you have version which has the value of 4. Okay. And the internet header length, it denotes the length of the outer header in 32-bit words. It denotes the length of the outer header in terms of 32-bit words. How many 32-bit words it contains. Okay. And TOS, uh, it is just copied from the inner header. Whatever the value of inner header, the same thing will appear in the outer header also for TOS. Okay. And length field, it covers the complete encapsulated packet, the length of the entire packet in bytes. Okay. So the field, there is a field, the fields up to TTL have no special meaning for mobile IP. Okay, they are very generic, normal IP packet fields. They don't have any special meaning for uh, mobile IP. Okay, TTL must be high enough. TTL must be high enough so that the packet can reach the tunnel endpoint. Okay, TTL represents time to live. It will be keep decrementing. If it becomes zero, the time the packet will expire. So TTL should have reasonably high value so that the packet can reach the tunnel endpoint. So and then uh, okay. So and the next field is denoted with IP, and IP in IP is the type of the protocol used in the IP payload. Okay, so what protocol here we are using? In the IP payload, we are using IP in IP protocol. Payload represents data port. Okay, so this is set to 4. The value of IP in IP will be set to 4. Okay, the protocol type for IP4, because 4 represents IP4. Okay, and the IP checksum is for error checking, and the next fields are tunnel entry as source IP address. The source IP address is IP address of HA, and the destination IP address is IP address of COE, care of address. Okay. If no options follow the outer header, if there are no optional fields, then the inner header starts. So immediately after the source IP address and destination IP address of the outer header, then the inner header starts. Okay. So what the inner header contains? The the inner header, it, it it's almost unchanged during encapsulation. Okay. So here uh, here the source address is the original sender CN. The sender is the address of CN, and the receiver is the address of MN. Okay. The only change here is the TTL will be decremented by 1. The TTL will be decremented by 1. This means that the whole tunnel is considered as a single hop from the original packet's point of view. The whole tunnel will be considered as a single hop from the original packet point of view. Okay. So this is important because it allows the MN to behave as if it is attached to the home network. No matter how many real hops the packet has to take in the tunnel, but logically it is just one hop away. for the MN. Okay. So anything it will, so this tunneling feature, it makes the mobile node to feel as if everything is close to it, as if everything is logically one hop away from it. Okay. And finally, the payload follows the two headers. Payload is the actual data part. So this is about IP in IP header. Similarly, we have another header which is minimal encapsulation header. Okay. And then there is another header called generic routing encapsulation header. Generic routing encapsulation header. The IP in IP and minimal encapsulation header, they work. Uh, IP in IP encapsulation and minimal encapsulation, they work only for IP. Whereas generic routing encapsulation, it supports other network layer protocols in addition to IP. So in addition to IP, it also supports other network layer protocols. Okay. So this allows the encapsulation of packets of one protocol suite into the payload portion of a packet of another protocol suite. Okay. So you can see the diagram here. So this is the original packet which has the original data and an original header. Okay. And then this is encapsulated with some other which is called as GRE header. So this means this header format and this header format are different. They are not same. They are totally different. Okay. And then this entire thing is considered as data part, and this is encapsulated with another header, outer header. And again, this is also totally different from this GRE header. Okay. So this type of encapsulation, uh, where, uh, where different formats of data can be encapsulated. Okay. So this type of encapsulation is called as generic routing encapsulation. It is the packet of one protocol suite with the packet of another protocol suite can be encapsulated. Okay. So yeah, so here you can see the diagram which shows the generic routing encapsulation. Uh, so basically, uh, this communication is between the home agent and COA using GRE, generic routing encapsulation, as an encapsulation scheme. Okay. The outer header is the standard IP header. Here the outer header is a standard IP header with HA as the source address, this home agent as the source address, and COA care of address as the destination address. The protocol type used in this IP header is 47. The protocol header used is 47. The protocol type used in this outer IP is 47, which represents GRE, generic routing encapsulation. The other fields of the outer packet are TTL and TOS. So this can be just copied from the inner header. This can be copied from the original IP header. Okay. But TTL should be decremented by 1 when the packet is decapsulated to prevent indefinite forwarding. Okay. When it is decapsulated, the TTL should be decremented by 1. So and the GRE header. So there are two types of header. Okay, one is the uh, uh, IP header. The top one is basically IP header. The next header is a GRE header. Okay, generic routing encapsulation header. It starts with several flags indicating if certain fields are permitted or present or not. Okay. A minimal GRE header uses only 4 bytes. A minimal GRE header uses only 4 bytes. GRE is flexible enough to include several mechanisms in its header. So, so it includes several mechanisms in its header. So it is considered as quite flexible. Okay, the C bit indicates if the checksum field is present and contains valid information or not. So there are many bits in the GRE header. So at first there is a C bit. So the C bit indicates if the checksum field is present and contains valid information or not. Whether there is a checksum field or not and it has a valid information or not. Okay. If the C bit is set, the checksum field contains a valid IP checksum of the GRE header. Okay. If it is set, then it means that then it means that the checksum field contains a valid IP checksum of the GRE header and the payload. The orbit indicates if the offset and the routing fields are present and and contains valid information or not. The orbit indicates if the offset and routing fields are present and contain valid information or not. The offset represents the offset in bytes for the first source routing entry. Okay. The routing field, if present, has a variable length and contains field for source routing. Okay. The routing field, if it present, has a variable length and contains a field for source routing. If the C bit is set, the offset field is also present. If the C bit is set, the offset field also is uh, present. Okay, and vice versa. The orbit is set. If the orbit is set, the checksum field must be present. Okay. If C bit is set, the offset field is also present, and vice versa. If the orbit is set, the checksum field must be present. Okay. The only reason for this is to align the following fields to 4 bytes. The checksum field is valid only if C is set, and the offset field is valid only if R is set. Okay. Only if C is set, the checksum field is valid. Similarly, only if R is set, the offset field is valid. Okay. So this GRE, generic routing encapsulation, also offers a key field which may be used for authentication. It also uses a key build which is used for authentication. Okay. If this field is present, the k bit is set. If this field is present, that is if the key field is present, then the k bit will set. However, authentication algorithms are not further specialized by GRE. The sequence numbers, the sequence number bit S indicates if the sequence number field is present or absent. The sequence number bit S indicates if the sequence number field is present. If the S bit is set, strictly source routing is used. Okay. Sequence numbers may be used by uh, sequence number can be used by decapsulator to restore packet orders. This is done in fixed network also. So this can be important. It's if a protocol guarantees in order transmission in encapsulation uh, and transferred using a protocol which does not guarantee in order delivery. Okay. So if a protocol guarantee in order permission in order transmission is encapsulation and transferred using protocol which supports encryption in order delivery. Now the decapsulator at the at the tunnel exit must restore the previous questions. Must restore the previous questions. Must restore the sequence to maintain the characteristics of the protocol. So next we will be discussing the resource control field. Resource control field is an important field at the additionality distinguishes GRE and IP in IP and minimal encapsulation. Okay, so the recursion field is an important field that additionally distinguishes GRE from IP in IP and minimal encapsulation. The field represents a counter that shows the number, and the field represents a counter that shows the number of allowed recursive encapsulations. Okay. So let us stop here. So this is about tunneling and encapsulation. So tunneling means sending the packet to the tunnel endpoint and exit point, and and uh, and encapsulation means keeping a packet inside the data packet of another packet is called as encapsulation. Taking a body out of encapsulation is called decapsulation. Okay, fine. Let us stop here. Thank you.